For 1 and 2, it's just asking in general what an electrophile and a nucleophile are. You don't have to give me specifics, but if you look at the notes, there are the slides specifically on electrophiles and nucleophiles. So a lot of times people will get these two terms mixed up. What helps is if you remember that like philic, so like hydrophilic, means that something is water loving. So phile, like phile, means that it likes it. So like an electrophile likes electrons. So when you're looking at an electrophile is a substance that wants more electrons. Right? It's an electron loving substance. And in the notes, it talked about different things to look for with electrophiles. Typically, it's going to have some sort of electron deficiency. So it could have a full positive charge. It could have a partial positive charge. It could have an incomplete octet. So maybe something only has 6 electrons instead of 8. And then in the video, also talked about a very polar bond. So if you have a bond like HF, that's very polar. And so that hydrogen actually has a pretty strong partial positive charge. So an electrophile is something that wants more electrons, right? It loves electrons. And then a nucleophile, again, phile means that it loves something. That means it loves the nucleus, right? So if you're thinking about a nucleophile, that's a substance that has a lot of electrons that's attracted to the nucleus. So a nucleophile is something that is attracted to the nucleus. So it's something that has a lot of electrons. In the notes, it talked about how it could have a fully or partially negative charge. So it could have a lot of excess electrons. You could look for lone pairs. When we talk about excess electrons, you could be looking at pi bonds, so double and triple bonds. Right? Those are excess electrons that can be used to attract a nucleus of another atom. Or it could be used to move a bond to a lone pair. So electrophile is a substance that wants more electrons. A nucleophile is something that wants to give its electrons to the nucleus. It loves the nucleus. And then one of the questions on the video was, do we always have to identify the electrophile and the nucleophile? No, you don't have to unless it asks. Right, so you want to be able to recognize, because when we start talking about different types of reactions, we might see something that's called a nucleophilic attack. So you want to make sure you know which one is which. So in 3 and 4, they each have, right, one of them is a nucleophile, one of them is an electrophile. And so you just want to look. Notice how on this first one, on number 3, there's this positive formal charge and negative formal charge. So that doesn't mean that it's like fully positive, fully negative like an ionic substance. It just means that this carbon has a positive formal charge, this oxygen has a negative formal charge. Remember, with organic, formal charge is going to be really important. We talked about formal charge yesterday. We'll continue to look at formal charge today. So with this, we notice that there's this positive, right? And so if you think about the positive, that means that it wants electrons. Right? If it's positive, it wants electrons. And so you don't have to redraw this necessarily. You could just put E, comma, N. Right? So the electrophile comes first, then the nucleophile. So this is the electrophile. So this hexane, because of this positive charge, it wants electrons here. Carbon doesn't want to have a positive formal charge. And so then that makes this OH, that makes this the nucleophile, right? This oxygen has that negative formal charge, which means it has more electrons than it technically would like, right? Technically, you want a formal charge of 0. And so the lone pairs, one of the lone pairs, this curved arrow is showing a movement of one of the lone pairs to this carbon. Now, you don't have to show the products or anything. We'll look at that today. But we do have, right, this being the electrophile, the OH being the nucleophile. And then with number 4, here we notice that there's a negative. Right? We don't see any kind of partial positive or anything on the HCl, but we do notice that the electrons are moving from this oxygen over to the hydrogen. And so since the oxygen has that negative formal charge. All right, this has this negative formal charge. That's going to have more electrons. It's attracted to the nucleus. It loves the nucleus. And so this is the nucleophile. This entire substance is considered the nucleophile. And then since this hydrogen is gaining electrons in some way, all right, it's gaining electrons in some way, this HCl is actually the electrophile. So nucleophile is something that has too many electrons. It's attracted to the nucleus. And then the electrophile is something that wants more electrons. It loves electrons, right? So it wants more. So for number 4, you could just put N, comma, E. So just looking more with the definition of nucleophile and electrophile. Any questions on the do now? No. So for this, we're going to be practicing looking at curved arrows. So that's what a lot of this practice is looking at curved arrows. Just a reminder about curved arrows. We're going to be looking at 3 options for curved arrows today. Right? And notice this is just like in the notes, the lone pair to lone pair is crossed out because you cannot do that in one step. We're always with curved arrows looking at a single step. Now you could have 2 curved arrows, but when we're talking about it, we're looking at just from one arrow, right, from the tail to the head of the arrow, what type of movement is that? And so we have lone pair to bond, which we'll look at. Bond to lone pair, so obviously you're taking electrons from a bond and you're making it into a lone pair, and then you have bond to bond. So maybe you're taking the electrons in a double bond and you're moving it to create a single bond. That's just a bond to bond movement. With the curved arrows, and you'll be looking at some of the mechanisms today. In the video, I tried to add some extra kind of notes. It's really important that when you draw your curved arrows, you are very specific about where the electrons are coming from and where they're going. So the tail should always point to some electrons, whether it's a bond or whether it's a lone pair. And then the head of the arrow needs to show where they're going. Make sure you are specific also about where they're going. They cannot just disappear into space. If they're going to create a lone pair, you need to make sure the head of the arrow is pointing to the atom. If they're creating a bond, make sure you're showing, right, where they're going to create that bond. And again, we're going to look at some of these examples today. So here's the first one. This is a lot of drawing, and I know drawing in Pear Deck might be a little bit more difficult, but just, do your best to draw. So for this, you are given a curved arrow already. So you are given the curved arrow that shows your electrons going from this bond, and they're pointing to the chlorine, which means it's going to a lone pair. So what you have to show over here is the outcome. So what are going to be the 2 things that you're going to have after this movement of electrons? So you should have 2 things. And if you need to flip back to, right, like the practice and the how to draw curved arrows, it kind of shows you, but we'll look at this as well. Good, and I see some people already are paying attention to formal charge as well. So essentially you're saying, okay, if these lone pairs in this bond are moving to chlorine, so now you're essentially, this bond will no longer exist. I don't want to say you're getting rid of electrons because that's not what you're doing, but this bond will no longer exist because these electrons, this bond has moved to a lone pair. And so what you're actually going to get is you're going to have this central carbon now only connected to 3 things. And then you're going to have this chlorine now with 4 lone pairs out on its own. So this chlorine is kind of leaving this alkane. All right, so if we take a look at just a couple and then you can continue drawing it. All right, so notice the chlorine leaves. The chlorine is leaving because this bond no longer exists. So you have 2 things. All right, you have 2 things afterwards. You have this alkane, and notice that here on both of these, the carbon, that central carbon, is labeled with a plus. Carbon always wants 4 bonds. If it doesn't have 4 bonds, it's going to have a positive formal charge. This is called a carbocation. It's carbon, that's a cation. So carbocation. So this positive formal charge goes with this central carbon. And then chlorine, normally chlorine has 7 valence electrons. Now it has 8, so it has that negative formal charge. This chlorine we'll talk more about when we get into different types of reactions. This is called a leaving group. All right, the chlorine is leaving that substance. And so you have these 2 things. So you have this carbocation plus this chlorine. Now, I'm going to show another one. Let's see, did anybody do it? Yeah. All right, so here's another one. All right, this one here. Notice the lone pairs aren't shown, but that's okay. All right, you don't have to show the lone pairs on that Cl. If you show one lone pair, though, you need to show them all. But you could just put Cl with that negative, because remember, by putting that negative, that's telling us chlorine now has 8 valence electrons. So both of these are correct.
Do we have to have that plus there to show
like that you're adding them together?
Yeah.
You should. I mean, if you have 2 things, you should show the plus in between. If you didn't right now, it'd be okay. But you want to get in the habit just when you're showing mechanisms, because that's like having 2 products. But this is just how you're showing that movement of electrons. Right? So again, this is showing, notice how on the answer key slide, I didn't show those lone pairs. That's okay. If you want to show them, that's okay too. But you have to show the formal charges. Right? Make sure you get in the habit of showing those formal charges. Okay, so now this one has 2 curved arrows. All right, 2 curved arrows. So first, think about the types of movement. Right? What are the 2 types of curved arrow movements that are happening here? And then actually show the products. You should have 2 products here. Remember, on any kind of organic substance, you have to show the atoms that are not carbon. So that means that you don't have to show all of the C's, but you need to make sure you're showing the O's, the H's, well, the H that's on the OH, and the Cl's. And then do a quick check of formal charge. All right, when you're done, do a quick check of formal charge to make sure. I'll give you a hint here. Only one atom is going to actually have a formal charge. So think about which one atom that might be. Good. So I see a lot of people that showed first this movement. So I'm going to try to continue to talk about the movement of curved arrows and which one of those three types it is. So for this, notice how the tail is coming directly from one of the lone pairs. So it's showing exactly where it's coming from. So you have the lone pair pointing now to the bond. So this is a lone pair to bond movement. So you're taking one of these lone pairs and now you're creating a double bond. Well, now this carbon has too many atoms around it because now it would have 5 bonds, which is why now you have the bond moving to a lone pair. So that's why when we talked about that lone pair to lone pair, technically that's what this is, but it's in 2 steps. So when we talked about curved arrow movements, we're talking about single step movements. So here we have a lone pair to a bond, then we have a bond to a lone pair. So if we look at some of the responses, right, and I know they're small up here, but notice how these have the double bond. And the reason that I picked these is because they're all correct and they still look a little bit different, right? Notice these first 2 show the lone pairs. This one doesn't. This one's still correct because it's showing the most important thing, which is the formal charge. And so what we have with this is we have now, right, this double bond. This is now carboxylic acid. So we have a double bond, and then we have that Cl that has left. So we take this single substance by moving the electrons around using those curved arrows. Now we've created 2 different products. Right? So what this is showing, this is just looking at the mechanisms of the curved arrows. Right? So let's look at this one. So now we have an alkene. All right, we have that double bond. So with the double bond, notice that you have electrons from the double bond. So that's that pi bond. You have these 2 electrons from the double bond pointing directly to the H. So this is actually a bond, and it's going to create another bond. So it's bond to bond, and then you have bond to lone pair. A hint for this one, you're going to have 2 formal charges that you need to show. Right? 2 formal charges that you need to show. Well, when you take this hydrogen, right? So you take this hydrogen, that's now going to bond the hydrogen to here.
Oh, it's bonded. Okay.
So this carbon right here is going to have the CH3 and then a hydrogen.
So it's 1 molecule.
Now this carbon is missing one of those 4 bonds. Mm-hmm. And then these electrons from the bond in the HBr are now going to create a lone pair. Now with this one, you could actually think about which one's the nucleophile and which one's the electrophile, right? Because one of them has excess electrons. It's doing the attacking. Nucleophile always does the attacking. And then the electrophile wants the electrons.
Can you see, like, can you see?
Me?
Yeah.
Yeah. Yeah, don't forget the BR.
Wait.
Oh, you're still working.
Right. Oh my lord, I can't draw.
Um,
Now.
Yeah, the positive, though, is going to go on, like, H wants one bond. That H has a bond. The positive is going to go where you're missing a bond.
Wait, so right here?
Yes.
Oh, cat is right there. But everything else is right?
Yep.
Wait, so it always goes where there isn't a bond.
So, okay, yeah. So let's look at a couple of these. And here's how it's going to help with formal charge. If you have the bond-to-bond movement, which is what this is showing, you have electrons from this double bond pointing to the hydrogen. That means that it is going to create a bond with the hydrogen. So that's the bond-to-bond movement. When it creates a bond, it's going to create a bond between one of these carbons and the hydrogen. So notice how both of these show that hydrogen. And the reason that showing the hydrogen for this is useful is because now you can see here, right? Okay, so now we have this carbon attached to the hydrogen, attached to the CH3, attached to the C. This carbon is missing, right, that additional hydrogen. And so that's why this is now that positive formal charge, right? The BRs are both negative, right? We didn't show the lone pairs, that's okay. But if we take a look at this, right, so it looks like this. These two, you could have it drawn either way. They're symmetric, so it doesn't matter which carbon you draw it on, right, because they're both symmetric. But when carbon loses a bond, right, when a carbon loses a bond, it's going to have a positive formal charge. So for this is a bond-to-bond movement. You're creating a new bond. This is a bond-to-lone pair movement. So this is just showing how these mechanisms are creating new products just by moving the electrons. Okay, so here's another one. So you have, notice again, it's showing exactly the movement of electrons. So this lone pair is moving to the hydrogen, meaning it's creating a bond. Right? When it's pointing to a hydrogen, it's going to be creating a bond. So this is creating a bond with hydrogen. Now these electrons in this bond are moving directly to the oxygen. So it's moving bond to lone pair. So here we have lone pair to bond, bond to lone pair. And then pay attention to formal charge. You're going to have two formal charges. 1, 2, 3, 4, 5, 6. Yeah, two formal charges. Notice we're not affecting any of those carbons. None of these carbons are being affected. So that means that your lone pairs are going to be on the oxygen. Not lone pairs. Your formal charges are going to be on the oxygens.
No. But I'm also
Remember, for formal charge, you're just looking at, right, how many valence electrons does it have? How many electrons are around it?
well.
Right? Valence minus electrons around it is going to give you formal charge.
Can I have a hint? Are they both the same form?
No.
I did something wrong.
Because when you move this to the H,
Oh.
that's just creating that bond.
Yeah.
So now you're going to have 1, 2, 3, 4, 5 electrons around this oxygen. It normally should have 6. Now you only have 5. So 6 minus 5 for that one. So I see a lot of people in their responses, right, have the formal charges, right, kept that double bond. Let's take a look at, all right, what this is actually going to look like. Now, a couple things here. Okay, thing 1. You didn't have to show the bond here. If you just did OH, that's okay. Means the same thing. But showing the bond might help you with formal charge. So the reason this is positive is because, remember, you put a circle around it. Right? When you put a circle around it, count how many electrons are in that circle. To find formal charge, it's valence minus number in the circle. 1, 2, 3, 4, 5. So this is plus 1. Over here, right, you have 7 electrons around, so 6 minus 7 is negative 1. Usually we just see either plus or minus for formal charge. We're not usually going to see like -2 or +2 for organic. A lot of times it's just plus or minus. But again, this is a lone pair to bond movement. This is a bond to lone pair movement. So we have 2 different types of movements here. All right, now this one looks a little weird because this is, right, a different type of substance. All right, so with this one, we're looking at, this is an epoxide. And so for this, it's still pretty specific with where everything is moving. So for example, here we see the bond electrons here are moving to create a lone pair on the oxygen. Then this lone pair is pointing directly to the carbon, which means it's creating a bond. To give you a hint, you're going to have just one product. And do a quick check of formal charge. But typically, if you have something negative forming a bond, that's going to get rid of its formal charge. If you have something positive gaining some electrons, it's going to lose its formal charge. So again, you're going to have just one product. And by moving these electrons in this bond to the O, you're getting rid of that triangle look. Right? These electrons are now moving to the O, so that's opening up this structure. And I think for the most part, what I see people have might look a little bit different than when I show you the answers, but it still is like the same, it's just drawn a little bit different. But again, in terms of formal charge, if something negative, right, is creating a bond, so it's almost like it's getting rid of some of the electrons because now it's sharing electrons. It's more than likely going to get rid of that formal charge. Right? If it's gaining some electrons and it was positive, it's going to get rid of that formal charge. So here's what this is actually going to look like. Now, if you drew it differently, all right, some people's were a little distorted. That's okay. What I saw though was that you still had, right, this carbon connected to the O and the CH3, and it was also connected. So this carbon here, right, this first carbon is this carbon right here. This carbon, this lone pair is creating a bond with this carbon. So this bond right here came from the lone pair. Now, if you double check oxygen here, right, it still has these two lone pairs. We're just not showing it. So 2, 4, 5, 6 electrons around it. There's no formal charge anymore because it has 6 valence electrons. Then over here, this carbon is this carbon over here. This oxygen, right here, it only had one lone pair because of that positive formal charge. Now it has 2 lone pairs. There's 6 electrons around it, has 6 valence, doesn't have a formal charge. And so again, this was lone pair to bond, bond to lone pair. If you say, like, how do we know how many lone pairs it has? That's based on the formal charges that we were given initially. That helps us to identify how many lone pairs it would have. Okay, so here's the last one. So now it says complete the mechanism by drawing the proper arrows in each step. So here's a little hint. This first step here, right, this first step, you're going to have 2 arrows. So for this first step right here, I should see 2 arrows drawn. Essentially look and see, okay, what has to happen to get from what we have on the left here to what we have in the center? And then what has to happen here in the center to get what we have here on the right? So again, here's a hint. You're going to have 2 arrows in this first step. You're going to have 1 arrow in this middle step. You're not going to have anything over here because that's your final product.
Okay.
So what do you notice first about this first hexene and then this hexane? What do you notice happens? Okay, so the H must come over here, and notice that the double bond is gone, which means the electrons from the double bond must be moving to the H to create a bond. And then notice how the Cl goes off on its own with that negative formal charge. So that means that the H is going to bond here, and the electrons that are in here are going to move to the Cl. Now, if this Cl has the negative, how many lone pairs is this Cl going to have around it? All right, it's going to have 8 electrons, 4 lone pairs. To make this bond here, you're going to have one of the lone pairs moving. All right, it's going to look like this.